All right, we're going to continue reviewing for the test tomorrow. First problem is a pressure problem. Pressure is equal to gravity times density times height. All right, so this is pressure. And this gravity. So gravity is a constant, 9.807 meters per second squared. All right, so then you'll be given a density and a height, but you have to put them in the SI units. So meters is meters per second squared. That is the SI unit for gravity, but density, it's mass over volume. Remember, mass, SI unit is the kilogram, and your volume, the SI unit, is length times width times height. That is a meter cubed. And then your height has to be in meters. All right, and so when you have your SI units, then you're going to get the SI unit for pressure, which is the Pascal. All right, and so when you multiply all those together, you got your meters per second squared, you got your meters, and you're dividing by meters cubed. So you end up with a kilogram over meter second squared, and that is a Pascal. All right, so if you're given a gravity, density, and a height, you can find that pressure in terms of pascals. All right, and so we have a pressure given, and that pressure is 750 millimeters of mercury. All right, and then the question is, how high would the alcohol be if it were measuring the pressure? And so your alcohol, we have thermometers. We use mercury. Mercury is got Mad Hatter's disease. You get central nervous system problems. And so we have switched away from mercury in thermometers and have gone to alcohol. So if we try that with our barometer to measure pressure with alcohol instead of mercury, you'll see why we can't do this. When we calculate the pressure in height of alcohol. All right, and so our density of mercury is given as 13.6 grams per centimeter cubed. Our density of the alcohol is given as 0.9 grams per centimeter cubed. All right, so in this case, we know that the pressure, whether we're measuring it in mercury or we're measuring it in alcohol, is the pressure of the day. It's the barometric pressure. So it is going to be the same. So they are equal. All right, but how do we find the pressure? Again, gravity times density times height. One side is going to be all mercury. And on the other side, it's going to be gravity, density, and height, but it's going to be all alcohol. All right, so we have our density, and it's the same. And so since it is the same, we can divide both sides by the same number, and it is gone, 9.807 meters per second squared. So the density will cancel on both sides. All right, if we have then our density and height equal density and height, we do not have to convert these when this is our equation, because these just have to be the same units, and these have to be the same units. All right, if we were asked for the pressure in pascals, then we would have to convert those to SI units, but we're going to just cancel these out. All right, and so we are given the density of mercury, we're given the height of mercury, and we're given the density of alcohol. So we just have one unknown, is the height of the alcohol. All right, so since the units just have to be the same, I'm going to use the density units as given, 13.6 grams per centimeter cubed. I am not going to use millimeters, I'm going to use meters. So I'm going to convert that into meters. Milli is 10 to the minus 3. So that is 10 to the minus 3 meters of mercury. All right, and so that is a 0.750 meters of mercury. All right, and that is equal to the density that is given for your alcohol, 0.9 grams per centimeter cubed. Again, the units have to be the same so that when we divide, they will cancel. And now we have the height of the alcohol. So we simply divide by 0.9 grams per centimeter cubed. They cancel. 0.9 grams per centimeter cubed. You get your calculator. You push the buttons. You have 13.6 times 0.750 divided by 0.900. And you get 11.3 meters. All right, so 11.3 meters. That is a very, very high distance. You would be climbing a very tall ladder or going up many flights of stairs in order to find the pressure of the day. All right, you can't just sit in your lab and have 0.750 meters, 3/4 of a meter stick, and that's what we want. And so that's why we stick with mercury. And so that is a very high density liquid. It is a metal that is a liquid, very high density. And that works out very nice to calculate pressures. It could be done with alcohol, but again, you're looking at 11.3 meters of alcohol. The next one says, give this pressure in atmosphere. So this is a conversion you must know. We have 750 millimeters of mercury. If we want to convert this to atmospheres, you simply divide by 760 millimeters of mercury is 1 ATM. All right, and 750 is 3 sig figs. 750 divided by 760, and you get 0.987 atmospheres. All right, so you're going to do that conversion many, many, many times. The next question says, convert that to torr. And you need to know that a millimeter of mercury is the exact same thing as a torr. And so to convert that, it's very simple, 750 torr. All right, so a millimeter of mercury is the same as a torr. All right, then the last one is where we have to use our SI units because the last one says calculate the pressure in pascals. All right, and then the conversion factor is not given because you already use the pressure is equal to gravity, density, and height. Since the density and the height for mercury was given, you do not need the conversion factor. You simply have to put in your gravity, which is your 9.807 meters per second squared. Now your density was 13.6 grams per centimeter cubed. We have to do some work with that because that is not the SI units. All right, and so we have to get to kilograms. We have to get rid of grams. We need kilograms. K is 10 to the third. We have to get rid of the centimeter cubed, and we have to get the meter cubed. C is 10 to the minus 2, and we have to do that 3 times. So write it out 3 times, or you cube it. All right, and when you push the buttons on that, you get 1.36 times 10 to the 4th. All right, and so your density in the SI units is 1.36 times 10 to the 4th kilograms per meter cubed. And we already converted our height of the mercury given into meters, and that was 0.750 meters. All right, and so when you put those in the SI units and you push the buttons, your 9.807 times 1.36 times 10 to the 4th times 0.750, you get 1.00 times 10 to the 5th. 1.00 times 10 to the 5th pascals. All right, so now we know that this pressure, this is your pascals, so we know that 1.00 times 10 to the 5th pascals is equal to 0.987 atmospheres. All right, so that's the pressure using the millimeters of mercury. We converted it to atmospheres because we have memorized that conversion. All right, we did not memorize the conversion to pascals, but that's why we were given a density and a height. We can just calculate the pascals. So if we wanted the conversion of pascals to atmospheres, we get rid of the 0.987 by dividing both sides by 0.987. So then we divide this by 0.987, and we get that the conversion factor of pascals to atmospheres is 1.01 times 10 to the 5th pascals is equal to 1 ATM. All right, so from this information, we can actually find the conversion factor of pascals to atmospheres because all of these pressures are exactly the same. All right, so this pressure in pascals is the same as this pressure in torr, which is the same as this pressure in atmospheres, which is the same as the pressure in millimeters of mercury. All of these are the same. And then another pressure would be meters of alcohol. So you would have meters of alcohol, also that same pressure. All right. Number 2 on this sheet. Is a gas law problem. It says we have 20 mils of CO2. At 23 degrees Celsius and 1 atmosphere. And the question is, what's the volume at STP? All right, so this is a very simple problem. Make my own problem up. All right, so you have, when you have STP, all right, you have to know, I usually write a 0,1 next to my STP so I don't mess it up. Because when you see standard temperature, many people will say, oh, that's 25 degrees. That is not correct for gases. The standard temperature and pressure is 0 degrees Celsius, 1 ATM. All right, but so now we see that what we are doing here is a constant pressure. Since we had 1 ATM and we're going to STP, which is also 1 ATM, you have constant pressure. All right, and so you end up with Charles's law. And that is V1 over T1 is equal to V2 over T2. All right, so I'm going to call this one part A. All right, now the key here is not up here because these just have to be the same. This is where everyone gets it wrong, but at STP, you can't get it wrong unless you put undefined as your answer, because if you put 0 degrees Celsius in the denominator and you push the button on your calculator, it will tell you that is not the right answer. All right, it will not give you an answer because that is undefined. All right, again, for the millionth time, temperature must be in Kelvin. All right, so you can do the problem, set it up all nice. If you put your temperatures in Celsius, you're getting 0 credit. I have said put your temperature in Kelvin way too many times. If it's not in Kelvin, you're not getting any points. If you put it in Kelvin, this is a simple, easy answer. All right, so volume 1, we started at 20 mils. Temperature 1, 23, you must add 273.15 to get 296 Kelvin. All right, volume 2, that is the question. That is what we want to know. And we see that we are now at 273.15 Kelvin because we are at STP. All right, and so when your temperature goes down, you have your balloon, you go outside and it's very cold, you know the balloon is going to shrink. So your volume is going to be smaller. It is a good idea to think that way on the test just in case you mess up the math. Don't give a volume that's larger you have gone to a colder temperature, and so your volume must be smaller. All right, to solve this, very simply multiply 273.15 to both sides. 273.15 to both sides. So you take 273.15 times 20 divided by 296, and that will give you 18.5 milliliters. All right. So I could have chosen a different circumstance for that. All right. I could have said, what's the volume at 23 degrees Celsius and 746 millimeters of mercury. All right, so I'm back up to the top. Okay, I have 20 mils of CO2 at 23 in 1 atmosphere. Now, what is the volume at 23 degrees Celsius and 746 millimeters of mercury? Now we see that our temperature has not changed. So this would be a constant temperature. And so that is Boyle's law. That is Boyle's law, all right? And so that is a P1 V1 is equal to P2 V2. So pressure 1, and they, again, here there's no temperature, so they just have to have the same units. All right, so if I want to work in millimeters of mercury, P1, 760 millimeters of mercury. So I either have to convert 1 atmosphere to millimeters of mercury, or I convert 746 to atmospheres. It doesn't matter. It will give you the exact same answer. All right, so again, P1, 760 millimeters of mercury. It said 1 atmosphere. That is 760 millimeters of mercury. The volume was 20 mils. What pressure do we have now? And that is 746 millimeters of mercury. And what is the volume now? So now we see that our pressure went down. So we have a lower pressure. All right, to get a lower pressure, the piston comes up, the volume is larger. Pressure volume inversely proportional. You increase the pressure, you're pushing down, you're going to decrease the volume. You decrease the pressure by pulling it up, then you increase the volume. So we're going to have a volume higher than 20. So 760 times 20 divided by 746, and we have a 20.4 milliliters. All right, let's do a lab question. All right, in lab, we are going to take 50 mils of 1 molar HCl, and we're going to mix that with 0.2 grams of magnesium. And we're going to do a single replacement reaction. So the magnesium reacts with the HCl to produce magnesium chloride and hydrogen gas. All right, and so to balance it, we have a 2 here. All right, and so when we do this, we're going to put it in our calorimeter. So 2 styrofoam coffee cups, we have a cardboard lid, we have a thermometer. All right, and so there is our thermometer. All right, so our temperature initial is 20.2 degrees Celsius. Our temperature final is 28.2 degrees Celsius. All right, and so the question here is to calculate delta H for this reaction, for this data. All right, so if you go to table 6.2 and you get the delta H, that is not what this is. This is in lab. All right, and our lab could be completely wrong, and that number could be completely different because maybe we didn't add 0.2 grams. Maybe it was 2 grams. We had some experimental error. There's always experimental error. So if you get this answer by the table, the chances of that being the correct answer is slim to none, because this is a lab which has a lot of error. All right, so we have to do this by taking our delta H and knowing our delta H is equal to Q over N. All right, and so we need the heat of reaction. So Q is the heat of reaction. All right, and N is the moles of MgCl2 produced. All right, you could use moles of H2 produced. That would probably be easier. But anyway, well, it doesn't matter. It's the one that has the coefficient of 1. So we want this in order of per mole of MgCl2. All right, to find Q. So we have Q gained is equal to Q lost. So heat gained is equal to heat lost. All right, so this reaction we know by the temperatures. So again, the beginning temperature was 20.2 degrees Celsius. The final temperature was 28.2 degrees Celsius. So we know that when we mix those together, we got an exothermic reaction. It got hot. The temperature went up. All right, and so this is the heat lost by the reaction. All right, so it's an exothermic reaction. Heat was released by the reaction. The heat was gained by the solution, and we detected that with the thermometer. So the solution gained the heat, and that was measured by an increase in temperature. And that increase in temperature was occurring because it was an exothermic reaction. The reaction was giving off the heat. All right, and for this, we're going to say that we have a perfect calorimeter, which again, that's experimental error. No calorimeter is perfect, but we're going to say that we're not going to have any calorimeter correction. The heat gained by the solution was exactly all of the heat that came out of the reaction. Again, you're going to have some heat loss to the surroundings with your calorimeter, but we're going to ignore that. It's a small number, and we're just going to go with that's going to be some more error in our data, in our experiment. All right, so to find the heat gained by the solution, the specific heat has to be given. And so the specific heat of a dilute acid is the same as water, 4.184, and that is in joules per gram degree. And the density is also the same as water. The density of the solution is 1.00 gram per centimeter cube or gram per milliliter. All right, so what we have for Q is MS delta T. We need the mass of the solution. We have the 50 mils, and we were given the density of the solution of 1. And so it is 1.00 gram per milliliter. And so you don't really have to show this. 50 mils is 50 grams. And so we have our 50 grams of solution. Our specific heat of the solution is the same as water, same as the density is same as water as well. 4.184 joules per gram degree. And that's why we didn't want the SI unit, because that's gram, that cancels that gram. All right, so now we need a delta T, and here's where people would get confused. So anytime you have a T, you should always convert that into Kelvin, and that will never be wrong. In this case, you would not have to convert it to Kelvin to get a delta T. So if you remember that delta T is the same whether you are in Celsius or Kelvin, you see that your delta T is going to be 8. All right, and so you have to be careful with the sig figs there, because you have 1 decimal and you subtract 1 decimal, and so it's going to be 1 decimal for your answer, and that's 2 sig figs. All right, so you're going to take your 50 times the 4.184 times the 8.0, and you will have the heat of solution. And so Q here is equal to the 2 sig figs, 1.7 times 10 to the third joules. All right, so that is the heat gained by the solution, which is equal to the heat lost by the reaction. So that is equal to negative 1.7 times 10 to the third joules. This is your heat lost by the reaction. Here is the heat gained by the solution. All right, and we say we're not going to lose any heat to the calorimeter, anything to the surroundings, and so we are putting in that amount of air. All right, so again, our delta T is temperature final, which was 28.0 or 28.2 minus the temperature initial, 20.2, 8.0, and you say that's Celsius. All right, so then you add your 273.15. And so your initial temperature is 301.4. And then your initial temperature, you add 273.15 and you have 293.15 or 0.4, 1, 5, and 2. And then you subtract those and you get 8.0. So it doesn't matter if you are in Celsius or Kelvin when you do your delta T. All right. To be safe, you may want to say, as soon as I see my 28.2 and my 20, I'm going to convert it to Kelvin. And then when I put in my delta T, I still get 8. That would be great. Or you just remember that a delta T in Celsius and Kelvin will be the same. Either way is fine. It doesn't make any difference. But make sure you never use Celsius for just a T in any equation. If it is a delta T, you can use the 2 temperatures of Celsius. If it is a T and you're putting in 1 temperature, it must be in Kelvin. All right, so there is our Q. Now we have to do our N. N is going to be from our limiting reagent. And so remember how you get moles. Molarity times volume will give you moles. Mass over molar mass will give you moles. And in this case, we are going to do both of those. All right, we were given 50 mils of 1 molar HCl. All right, so this is our molarity times our volume to give us moles. But you have to know that your 1.00 capital M is not helpful. You have to put that as moles per liter. If you don't, you're going to have the wrong answer because you wouldn't convert your your 50 mils into 0.0500 liters. The only way to get liters is to convert this, and then you have to multiply them together to get your 0.0500 moles. All right, so that's your moles of your HCl. Now, the other one was 0.2 grams of magnesium. So you have your 0.2 grams of magnesium. That is a solid. Off the periodic table, we find magnesium. And that is 24.31. grams per mole. This one needs to be pushed on the calculator. 0.200 divided by 24.31, and that is a 0.00823. moles magnesium. All right, and so our balanced chemical reaction again was the magnesium plus 2 HCl yields MgCl2 plus H2. And so you have 2 reactants. You have to figure out which one of those is the limiting reactant. So we do magnesium. It is 0.00823 moles magnesium. And we see that that is a 1-to-1 mole ratio. 1 mole Mg will give 1 mole of MgCl2. And so that is 0.00823 moles MgCl2. All right, so now we take our 0.05 grams of HCl. Balanced chemical reaction, we see that we have 2 moles HCl to give 1 mole of MgCl2. And so that is a 0.0250 moles of MgCl2. So remember, when you're doing the theoretical yield, the limiting reagent, it is the one that produces the least amount of product. And so this is your theoretical yield, and your Mg is your limiting reagent. All right, and that is the number you're putting in for your N. So now to find delta H, it is going to be Q divided by your N. All right, and so you have your Q value, which was 1.7 times 10 to the third joules. If I remember correctly, delta H, again, we are simply doing Q over N. N is the limiting reagent in moles. 0.00823 moles. All right, and so when you divide those two numbers, that is going to give you the heat of reaction. And again, to find your percent error, then you would go to your table 6.2 to get the actual answer that you should have gotten in order to find your percent error. All right, so let's push the buttons. You got your negative 1.7 times 10 to the third joules divided by 0.00823 moles. And we get a negative 2. We'll just say negative. Yeah. So that is a negative 2.1 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th joules per mole. All right, and so that's how you find the delta H for that reaction given experimental data. Heat gained by the solution is equal to heat lost by the reaction. All right. Let's try the next problem here, and let's do number 6. Okay, I like this one. You got C3H8, and that is a gas. You've got oxygen, that is a gas, that produces CO2, that is a gas, and H2O. And at this temperature, that is also a gas. So we're at a temperature that is above 100 degrees in order for that to be a gas. All right, so first thing we want to do is balance this reaction. So anytime you're given a reaction, make sure it's balanced. And when you have 3 carbons on this side and only 1 on this side, you do not have a balanced chemical reaction. All right, so you have to have a 3 in front of the CO2. You got 8 hydrogens here, and so you need a 4 in front of your H2O. And then on the left side here, we've got 6 oxygens and 4 oxygens, 10 oxygens. And so you would have a 5O2. All right, and so for this one, note everything's a gas. And so we can use mole ratios. We can also use volume ratios. And so we're going to take 10 liters of our C3H8, 10.0 liters of our C3H8, and we're going to take 40 liters of oxygen. All right. And then 22 liters of CO2 was collected. All right, and so the question is to calculate your limiting reagent, theoretical yield, and percent yield for this problem. All right, and so in this, no temperature and pressure was given. A temperature and pressure could be given. They're all the same temperature and pressure, and so you could convert that to moles and then do the mole ratio. If a temperature and pressure is not given, you do not need it because these are all gases. And so you would say that you have 10.0 liters of C3H8. And since it's all gases, the volume ratio is 1 liter of C3H8 is going to produce 3 liters of CO2. All right, again, you can only use volume ratios when every reactant and every product is a gas. So this would produce 30.0 liters of CO2. You have to do the same thing with your oxygen, 40 liters of oxygen. And now you have your volume ratio since everything's a gas. You've got 5 liters of O2, that would produce 3 liters of CO2. All right, and so that is 120 divided by 5, 24 liters of CO2. So again, just like we did the last time, the limiting reagent and theoretical yield are from the one that gives you the lowest amount of product. So that is your theoretical yield, and oxygen is the limiting reagent. All right, and so then the percent yield, it said we got 22 liters of CO2. So remember, percent yield, actual, what you got in the lab, over theoretical, times 100. So it said we collected 22.0 liters. The theoretical yield is 24.0 liters times 100. So you take 22 divided by 24, multiplied by 100, and you get a 91.7%. So that is a 91.7% yield. Right? Oh, number 8's a good question. All right. All right. What element has a density of 1.96 grams per liter at STP? All right, so we have a density, and we have a temperature and a pressure. And then when it says what element, then we know that we have to be calculating a molar mass. So if it's to identify an element, you have to have the molar mass, go to the periodic table, and you will identify the element. All right, that was a 91.3%. All right, so in this problem, which is number 8 on my page here, we have a 1.69 grams per liter. That's the density at STP. Identify the element. All right, so we have PV is equal to nRT. Again, in order to find moles, you take the mass divided by the molar mass, and that gives you moles. So we substitute that in. PV is equal to mass over molar mass, RT. Now we have, we need to solve for molar mass. Anytime it says identify the element, that means calculate the molar mass and then go to the periodic table and see what element that is. All right, so we solve for molar mass. Multiply both sides by molar mass. Divide both sides by PV. So that is MRT over PV. All right, note I put it as the V first and then the P. It doesn't make any difference. The reason why I did that is to see that that is your density. All right, because they gave us the density and they gave it to us in the right units. The density for gases that we're going to use in PV is equal to nRT, grams per liter. All right, so that is 1.69 grams per liter. The R value in PV is equal to nRT, always 0.08206 liter atmosphere per mole Kelvin. And your temperature at STP is 0 degrees Celsius. You always have to have a T in Kelvin, 273.15 Kelvin, and then divide by STP is 1 atmosphere. And so when you push the buttons, 1.69 times 0.08206 206 times 273.15 divided by a perfect 1. You get a molar mass of 37.9. All right, and so when you go to the table, boy, that is a interesting question. All right, and so this is in grams per mole. In this question, I didn't think it was relative, but it is relative. It says you have a reactive element. All right, and of course it is a gas. All right, it has to be one of the gases. And so if you're in Strebe and the periodic tables on the wall and you see all the red elements are gases, so it's got to be one of the red elements. All right, and so when it says reactive, what that means, it is not a noble gas. Noble gases are non-reactive. All right, and so argon would be a close choice. All right, if it didn't say it has to be reactive, argon's molar mass is 39.9, all right, grams per mole. All right, so that would be pretty close to this experimental data. The reason why that's not the answer is because it says right here it's a reactive. And so then you look at all of the other gases. And then nothing adds up to 37.9. Nothing is 37.9, but you've got to remember that when you're looking at hydrogen gas, it's not 1, it's 2. So it is not 1, it is times 2 of those, 2.00. And so when you're looking at oxygen, it's not 16, it's 32. All right, now we're getting closer. When we're looking at fluorine gas, it is not 19, it is times 2. And that is 38, and that is your answer. So this is fluorine gas. All right, so to calculate the molar mass would be a lot of credit. To then go and see that it is not the argon because it says it is a reactive gas, and your noble gases are non-reactive. You should not be picking a noble gas, and if you note that, then you have very few choices for the gas. The gases that are not noble gases, you've got your hydrogen, your oxygen, you got your nitrogen, which would have been 28, and then you got your fluorine and you got your chlorine, 35.45, so that would have been 70.9, and then that's it. Bromine's a liquid, and iodine's a solid. So that's it for the gases that it could be: hydrogen, oxygen, fluorine, nitrogen, chlorine. So those are the only ones that it could be. So that would be a multiple choice of 5 things. All right. So it says it has to be reactive. That means it is not a noble gas. All right, another one that is pretty much guaranteed to be on the test is one like this. All right, oxygen collected over water. At 23 degrees Celsius. Lab pressure was 758.3. All right. So, question here is calculate the pressure of oxygen. All right, and so your pressure of oxygen, every time you see this, collected over water. If you see that phrase, collected over water, you're going to be given a chart. And the chart, you're going to be given a couple of charts. They're on Moodle. Let's see if I can. But anyway, you're going to be given a temperature and pressure of water. So your pressure of water off of a table. What you're looking at is 23 degrees Celsius. You look on that table, 23 degrees Celsius. It says the pressure of water is 21.1 millimeters of mercury. All right, and so you have your two pressures. So your pressure of the lab is your pressure total. We collected our oxygen over water. And so your pressure of your oxygen plus the pressure of your water is the pressure total. All right, the lab is the total pressure, 758.3 millimeters of mercury. Pressure of oxygen, that's what we're solving for because we looked up in a table and found the pressure of water at 23 degrees Celsius is 21.1. And so our pressure of oxygen, when you subtract 21.1 from both sides, is 737.2 millimeters of mercury. All right, so then we can then calculate the mole fraction of oxygen and the mole fraction of water in the gas phase. All right, so here you have to solve for moles, so PV is equal to nRT. All right, so we will have the pressure. We got the pressure of oxygen. We got the pressure of water. So there's the pressure of water. Here's the pressure of oxygen. Volume. All right, we don't have a volume. We don't have moles. We have R, we have T. So without volume, you cannot solve for moles. And so how can you do a mole fraction? So you got to remember that when you're doing mole fraction, that is moles of, say, oxygen divided by moles total. All right, we don't have either one of those numbers. What you have to remember is that when you are in the gas phase, that is equal to the pressure of oxygen over the pressure total. We have both of those. All right, so the mole fraction is the pressure of oxygen, 737.2 millimeters of mercury, divided by the pressure total, 758.3 millimeters of mercury. All right, so that's how you would get the mole fraction of oxygen. Again, mole fraction of water, you would need the moles of water over the moles total. We don't have either one of those numbers. All right, but it is the pressure of water over the pressure total. We have both of those numbers. So that is the 21.1 millimeters of mercury over the 758.3 millimeters of mercury. And remember, fractions will add up to 1. If they were as percentages, the percent adds up to 100%. So when you take your 737.2 and divide by 758.3, you get a mole fraction of 0.9722. And when you take your 21.1 and divide by 758.3, you get a 0.028. And when you add those up, you get a 2 and then a 0 and then a 0 and then a 0 and then a 1. And then you say, I have 4 decimals. Should be another. I need 3 sig figs, 2, 7, 8. No, that's a perfect 0 then. All right, so you have 4 decimals, you have 4 decimals, you have 4 decimals. So that's a 0.0278. I have 3 sig figs, not 2. And so they add up to a perfect 1. And so that is what your fractions must add up to. All fractions added up has to be 1. All percentages added up has to be 100%. You have to know that a mole fraction in the gas phase can be found as the partial pressure of the gas divided by the partial pressure, or the pressure total. All the partial pressures added up. If you only know it by moles over moles total, you would not be able to do this problem. There is no way for you to get moles. I did not give the volume in that question. All right, let's try. Let's do speed, molecular speed, RMS speed, is the square root of 3RT over molar mass. All right, so if you calculate the speed, the RMS speed of nitrogen gas, at 22.2 degrees Celsius. All right, so here is a units problem. All right, so you have two R values. You got your 8.314 joules per mole Kelvin, and you got your R value given as 0.08206 liter atmosphere per mole Kelvin. All right, and so this one is not as clear unless you know, and you must know, what the units of the joule are. The joule is a kilogram meter squared per second squared. Because if you just look at joules per mole Kelvin and liter atmospheres per mole Kelvin, and you're looking for a speed, which you should know means a meters per second is a speed, how do you get meters per second from joules? Well, this is how you get meters per second from joules. And that also explains why you take the square root, because you have meters squared per second squared. We're going to take the square root. All right, so again, I am not very, you're not going to get any partial credit if you put the wrong R value in. Liter atmospheres is no way going to give you meters per second. You must use the correct R value, and that is all from the units. All right, so we have the square root of 3, and now I put in my R value, 8.314, and I'm going to put the units in as I need them, and that's these units. A kilogram meter squared per second squared, but it is still per mole Kelvin. All right, and then my temperature always has to be in Kelvin. If you put 22.2 in there, again, you're not going to get any credit. Anytime there's a T and you put in a Celsius, you're not going to get any partial credit. For delta T, you can use two numbers to put in for Celsius to get a delta T. But if it is just T, must be in Kelvin, 273.15. So that is a 295.4 to the correct sig figs, 295.4 Kelvin. And then there's a lot of tricky parts about the bottom one. One is it just says nitrogen gas. One thing you have to know is nitrogen is diatomic. So if you pick 14 as the molar mass, you got the wrong answer. All right, so it's 214. So this is 28.02 grams per mole. And if you put 28.02 grams per mole in for molar mass, you have the wrong answer. Because it is not grams that we need. It is kilograms that we need. And so you have to put in a 0.02802 kilograms per mole. All right, so again, you just have to get rid of grams, kilograms. All right, so you had to divide by 1,000. All right, so now you're ready to push your buttons on your calculator. You've got 3, which is part of your equation, times the R value, 8.314, times the temperature in Kelvin, 295.4, divided by your molar mass in kilograms per mole, 0.02802. All right, and so again, let's show the units canceling. Kilograms cancel kilograms, moles cancel moles, Kelvin cancels Kelvin. All right, and so if you forget to take the square root, then you have the wrong units, because right now, without the square root, it is meters squared per second squared. And so we must take the square root. And that gives us 2 looks like we need 4 sig figs. 512.8 meters per second. And so the speed of nitrogen gas at 22.2 degrees Celsius is 512.8 meters per second. All right, the other equations that we use for gases moving is effusions. All right. So here's an effusion question. Okay, it says 3.52 seconds for 10 mils of helium to effuse. It takes 9.95 seconds for 10 mils of, well, of what? Okay, so then we have to know what is this gas. All right, and so in order to find the gas, we're going to need the molar mass. And so our equation, so Z effusion of gas 1 over Z effusion of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. All right, so effusion rate is volume per time. All right, and so both of these have a volume of 10 milliliters, and both of these have the units of time in seconds. All right, so it doesn't matter what unit of volume you're using, but it has to be the same. It doesn't matter what unit of time you're using, but again, it has to be the same. So if they wanted to give them both in minutes or hours or days or years, it doesn't matter, but they have to be the same because you are dividing them. All right, and so we will change it. I'm going to say that my gas 1 is helium, first one I come to. And so I have the volume of helium over the time for helium is equal to the volume of the unknown divided by the time of the unknown. And that is equal to the square root of the molar mass of the unknown divided by the molar mass of the helium. So everywhere I had a 1, I put helium. Everywhere I had a 2, I put the unknown. All right, so now I can put in my numbers and solve my equation. All right, so the volume of helium, that was 10 milliliters. The time for helium was 3.52. The volume for the unknown gas was 10 milliliters. The time for the unknown gas was 9.95 seconds. The molar mass for the unknown, well, that's what we're looking for. The molar mass of helium, periodic table, and that is a 4.00 grams per mole. All right, and so then you push the buttons on your calculator. So what? All right, so your 10 divided by 3.52, and that divided by 10 divided by 9.95, and that gives you 2.83. Right, so this is, when you do this, you have 2.83, and that is equal to the square root of the molar mass of your unknown divided by 4.00 grams per mole. All right, so to get rid of the square root, you got to square both sides. So we have to square this side, and we have to square this side. I'm not going to clear my calculator because it is actually, the number here when you divide that is 2.8267. Yeah, okay. That's enough. All right, so I'm not going to clear my calculator. I'm just going to square it. And that gives me 7.99. So that is 7.99, and that's equal to the molar mass of your unknown divided by 4.00. All right, and so then we multiply both sides by 4. 0.00, and we get a 32.0. So the molar mass is 32.0 grams per mole. All right, then you go to the periodic table and you find a gas that has a molar mass of 32, or you just know that that's oxygen because you've done that a million times. This is oxygen gas. So 16 times 2, 32. All right. So we knew that the molar mass had to be larger than helium's molar mass because it took longer. So helium is smaller and faster. This one is going to be larger and slower to go through a hole. All right, and so we knew that the molar mass had to be greater than 4. In this case, it was 32, and that was oxygen gas. All right. Let's do write the reaction for delta H naught formation of HCl. All right, so I want you to write the reaction for delta H naught formation of HCl. So if you know the definition, this is a very simple question. If you don't, it's impossible. All right, so you have to know delta H naught formation is the formation of 1 mole from elements. So we have to form 1 mole of HCl from elements in their standard state, which means hydrogen and chlorine are both diatomic. In order to get that to be a 1 mole, you have to take 1/2 of the H2 and 1/2 of the Cl2. So you have to know the definition. If you know the definition, that is a simple question. If you don't, it is an impossible question. All right, let's calculate the delta H naught for this reaction, and it is 2H2S gas plus 3O2 gas, yielding 2SO2 gas plus 2H2O gas. All right, so when you're given a problem where it's just a reaction and it says calculate delta H, this is where you must use the chart. 6.2, I think, is the number. All right, so you look up your delta H naught formations. All right, H2S. There are 2 of them. Make sure you are very careful. Whichever one is, this could be aqueous or this could be gas. They're 2 different numbers. So for H2S gas, on the chart, negative 20.50 kilojoules. Oxygen is actually on the chart. It does not have to be on the chart. That is an element in its natural state. You should know that that is 0. SO2 gas, off the chart, negative 296.8 kilojoules per mole. And again, water will come gas or liquid. In this case, it was labeled as gas. Make sure you get the right phase. It is a different number if it is a liquid. For the gas, negative 241.8 kilojoules. All right, and so this is a very simple question. You should not be missing this. If you miss it, it should be because you pushed a button wrong on your calculator, not because you didn't know how to do it. It's simply the products minus reactants. So you have 2 times the negative 296.8 kilojoules plus 2 times the negative 241.8 kilojoules. All right, so you got 2 of these, you've got 2 of these. You add them up. That is the products. Minus the reactants. You have 2 of these. 2 times negative 20.50. All right, so you should be able to set that up. You can put 3 times 0 if you want, but that's 0. I don't care how many of you have, that is still a 0. All right, so when you push the buttons on your calculator, this is where the errors can occur, but you should at least be able to set it up. 2 times the negative 296.8 plus 2 times the negative 241.8. I would recommend putting a number there. That is negative 1077.2. Negative 1077.2 minus, and this one I can probably do in my head, yes, so that is minus a negative 41.00. All right, so push the buttons if you need to. That is a negative 41.00. And again, this is a minus and this is a negative. All right, and so then to the negative 1077.2, you're adding 41 in order to get your answer, negative 1036.2 kilojoules per mole for that reaction. So here's your delta H naught for that reaction. So products minus reactants. All right, and so then usually like in a part B, it would say I have SO2 plus H2O yielding H2S plus 3/2 O2. What is my delta H now for this reaction? All right, so you have to know what is happening from this reaction that we know the delta H for because we just solved it, and what is happening from here down to here. All right, you see that it has been reversed. The SO2 and the H2O, those are now reactants. When you reverse your reaction, you always change the sign of your delta H. And then we also divided everything through by 2. And so your delta H naught for this reaction is positive 1036.2 divided by 2, which is a 518.1 kilojoules. All right, so you take the, get that right. Should be right. All right, so you have to reverse it and divide by 2. And so when you reverse it, you change the sign. Now, remember, negative means that this is an exothermic reaction. Anytime you reverse an exothermic reaction, you have an endothermic reaction. This reaction gets hot. This reaction gets cold. If you're holding on to an exothermic reaction, your hand will feel hot. If you're holding on to an endothermic reaction vessel, your hand will get cold. All right, that test is tomorrow.